Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish, just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most profound questions in all of science. How far does the observable universe actually reach? We'll discover why this question has a specific, calculable answer that's different from infinity. How the expansion of space creates a cosmic horizon beyond which we can never see, and why the edge of what we can observe is not the edge of what exists. But don't worry, this isn't going to be an overwhelming journey through incomprehensible infinities or a dizzying plunge into conceptual paradoxes. Instead, we'll move slowly and thoughtfully through the ideas, building understanding piece by piece, finding clarity in what seems mysterious. By the end, I think you'll have a deeper appreciation not just for how far we can see, but for what that distance means and why it exists. If you enjoy these calm explorations of cosmic boundaries and the nature of space itself, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in now. Let your shoulders drop, releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand and release it gently. Feel yourself sinking deeper into comfort with each exhale, and let's begin our slow drift through the observable universe, exploring how far light has travelled to reach us and where the cosmic horizon lies. There's nowhere you need to be, no distances you must traverse. Just listen, and let the vastness unfold like space itself, expanding in all directions. Let's begin with the straightforward answer to our question, because understanding the complexity requires first knowing the basic number. The observable universe extends approximately 46.5 billion light-years in every direction from Earth. This creates a sphere with a diameter of roughly 93 billion light-years. This is the distance to the cosmic horizon, the farthest point from which light could have reached us since the Big Bang. The number might seem impossibly large, and it is. 93 billion light-years is a distance that exceeds human comprehension through direct experience or intuition. But it's a specific, finite number derived from observation and calculation. It's not infinity. The observable universe has a definite size, even though that size is unimaginably vast. This immediately raises a puzzling question. If the universe is about 13.8 billion years old, shouldn't we only be able to see 13.8 billion light-years in any direction? If light travels at a fixed speed and has been travelling since the Big Bang, simple multiplication suggests the observable universe should be about 27.6 billion light-years across, not 93 billion. The discrepancy is real and significant. The observable universe is more than 3 times larger than this naive calculation suggests. The resolution to this puzzle lies in understanding that space itself has been expanding during the time light has been travelling. The expansion of space stretches distances, and this expansion affects how far light can travel before reaching us. This expansion isn't like objects moving through pre-existing space. It's space itself growing, carrying galaxies along with it like raisins in rising bread dough. When we observe a distant galaxy, we're seeing light that left it billions of years ago when the universe was smaller. Since that light was emitted, space has expanded, increasing the distance between us and that galaxy. The galaxy we see as it was billions of years ago is now much farther away than the distance light travelled to reach us. This is why the observable universe is larger than simple light travel time would suggest. The exact size depends on the universe's expansion rate, how that rate has changed over cosmic history, and the geometry of space itself. Cosmologists calculate the observable universe's size using models that incorporate these factors. The 46.5 billion light-year figure comes from these detailed models, not from simple multiplication. This number represents our cosmic horizon, the boundary beyond which we cannot see, because light from farther regions hasn't had time to reach us yet. Beyond this horizon, the universe presumably continues. There's no reason to think space ends at the edge of what we can observe. The observable universe is just the portion accessible to our observations. Think of it like standing in a vast flat landscape. Your horizon extends a certain distance in every direction, determined by the curvature of Earth and your height above ground. Beyond your horizon, the landscape continues, but you can't see it, because light from those distant places can't reach your eyes, following Earth's curved surface. The cosmic horizon is similar but more fundamental. It's determined not by local curvature but by the age of the universe and the speed of light combined with cosmic expansion. The observable universe's size is thus fundamentally limited. No matter how powerful our telescopes become, we can never see beyond this horizon unless we wait for light from more distant regions to arrive. This creates a profound limitation on cosmology. We can only study the universe within our observable sphere. Anything beyond is forever inaccessible to direct observation. Yet this limitation is also liberating. It gives a definite scope to observational cosmology. We're not trying to understand infinity, but rather a large but finite region whose properties we can, in principle, measure. The 46.5 billion light-year radius represents the distance to the most distant objects we could possibly observe, if we had perfect instruments and could detect the faintest signals. In practice, we can't quite observe to this limit. The most distant light we've detected comes from the cosmic microwave background, radiation from about 380,000 years after the Big Bang. This radiation comes from approximately 46 billion light-years away in co-moving coordinates, very close to the theoretical limit. Galaxies, which formed later, can be observed to somewhat smaller distances. The most distant confirmed galaxies are about 13.5 billion light-years away in light travel distance, though much farther in current proper distance. The observable universe thus has a definite, calculable size based on the age of the universe, the speed of light, and cosmic expansion. This size is finite, though unimaginably vast by human standards. Understanding this basic answer provides the foundation for exploring the subtleties and complexities that make the question more interesting than it initially appears. One of the most confusing aspects of cosmic distances is the distinction between light travel time and actual distance, concepts that are equivalent in everyday experience but diverge dramatically on cosmic scales. When we say a galaxy is 10 billion light-years away, we might mean one of two different things, and distinguishing them is crucial for understanding the observable universe's size. Light travel time distance, also called look-back time, is how long light has been travelling to reach us. If we observe a galaxy whose light has been travelling for 10 billion years, we might say it's 10 billion light-years away in light travel time. This is the distance most people intuitively understand. Light travels at about 300,000 kilometers per second. In a year, it covers roughly 9.5 trillion kilometers, defining a light year. If light travels for 10 billion years, it covers 10 billion light years. This seems straightforward. But this distance doesn't account for cosmic expansion. During those 10 billion years that light was travelling toward us, space was expanding, stretching the distance between us and the galaxy. The galaxy that emitted the light 10 billion years ago is no longer 10 billion light-years away. It's much farther now because space has expanded in the intervening time. The proper distance, also called co-moving distance, is how far away the galaxy is right now, at this moment, accounting for the expansion of space since the light was emitted. This proper distance is larger than the light travel distance, sometimes dramatically so for very distant objects. A galaxy whose light has travelled for 13 billion years is currently about 32 billion light-years away in proper distance, due to expansion during those 13 billion years. The most distant objects we observe, emitting light just a few 100 million years after the Big Bang, are now about 46 billion light-years away, even though their light has travelled only about 13.4 billion years. This distinction is why the observable universe is 93 billion light-years across rather than 27.6 billion. The radius of 46.5 billion light-years is proper distance, not light travel distance. Understanding this distinction requires accepting that distances in an expanding universe are not static. The space between objects grows over time. When cosmologists specify distances to distant galaxies, they must clarify which distance measure they're using. Different questions require different distance definitions. For understanding how galaxies appeared in the past, light travel time is relevant. That tells us how long ago the light was emitted and what cosmic epoch we're observing. For understanding the current structure and size of the observable universe, proper distance is relevant. That tells us where objects are now, even though we see them as they were in the past. The relationship between these distance measures depends on the expansion history. If the universe expanded slowly, the difference would be small. The faster the expansion, the larger the discrepancy. Our universe's expansion has actually accelerated over time due to dark energy. This acceleration affects how proper distance relates to light travel time for very distant objects. In the early universe, matter dominated and expansion was decelerating. More recently, dark energy has dominated, causing accelerated expansion. This complex expansion history means the relationship between light travel time and proper distance is not a simple multiplication factor, but requires integrating the expansion rate over cosmic history. Cosmologists use redshift as a practical measure of distance. Redshift directly indicates how much space has expanded since light was emitted. A redshift of 1 means space has doubled in size. Redshift 2 means space has tripled. Very distant galaxies have redshifts of 10 or more, indicating space has expanded by factors of 11 or more. The cosmic microwave background has a redshift of about 1090, meaning space has expanded by a factor of roughly 1090 since that radiation was emitted. Converting redshift to proper distance requires knowing the universe's expansion history, encoded in cosmological parameters like the Hubble constant and dark energy density. These counterintuitive results all follow from taking cosmic expansion seriously and carefully tracking how distances change as the universe evolves. For the observable universe's size, we use proper distance measured at the present cosmic time. This gives the 46.5 billion light-year radius and 93 billion light-year diameter. This is the true current extent of the region from which light has reached us, accounting for all the expansion that has occurred since the Big Bang. The farthest light we can observe comes not from galaxies or quasars, but from the cosmic microwave background. Primordial radiation that reveals the universe as it was just 380,000 years after the Big Bang. This radiation defines our observational horizon more fundamentally than any discrete objects, because it comes from everywhere in the sky simultaneously, creating a sphere surrounding us. The cosmic microwave background, or CMB, was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who detected mysterious microwave noise in their radio antenna. This noise turned out to be radiation from the early universe, cooled by cosmic expansion from the intense heat of the Big Bang to just a few degrees above absolute zero. The CMB originates from the epoch when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, a process called recombination. Before recombination, the universe was opaque. Free electrons scattered photons constantly, preventing light from travelling far. The universe was like the inside of a thick fog. At recombination, electrons combined with protons, leaving few free electrons to scatter light. The universe suddenly became transparent, and photons could travel freely. The The CMB is the light from this transition, photons that were last scattered just as the universe became transparent. These photons have been travelling freely ever since, for about 13.8 billion years. Because recombination happened throughout space at roughly the same cosmic time, we can observe CMB radiation from all directions. Every point in the sky shows us a part of this primordial light. The CMB forms a sphere around us at a specific proper distance, approximately 46 billion light-years away. This sphere is often called the surface of last scattering. We cannot see beyond this sphere because the universe was opaque before recombination. Any photons from earlier times were scattered and absorbed repeatedly, never reaching us. The surface of last scattering thus represents a fundamental observational boundary, more absolute than our galaxy or cluster or supercluster boundaries. The CMB has been studied in exquisite detail by satellites like COBE, WMAP, and Planck. These missions measured the temperature of the radiation across the whole sky with incredible precision. The average temperature is 2.725 Kelvin, remarkably uniform, but tiny temperature variations exist, about 1 part in 100,000. These temperature variations, called anisotropies, are critically important. They represent density variations in the early universe that eventually grew into galaxies and large-scale structure. By analysing the pattern of temperature variations across the sky, cosmologists extract enormous amounts of information about the universe's composition, geometry, and expansion history. The CMB anisotropies tell us the universe is spatially flat, meaning parallel lines remain parallel over cosmic distances. They tell us the proportions of ordinary matter, and dark energy. They reveal the universe's age to high precision, roughly 13.8 billion years. They constrain the expansion rate and how it has changed over time. Perhaps most relevant for our question, the CMB defines how far the observable universe extends. The proper distance to the surface of last scattering is the maximum distance from which light could have reached us. Regions farther than the CMB sphere are beyond our observational horizon. Light from those regions hasn't had time to reach us yet. They're outside the observable universe. This doesn't mean those regions don't exist. Space presumably continues beyond what we can observe, but we have no direct information about regions beyond the CMB sphere. The CMB sphere itself is expanding from our perspective. As time passes, light from more distant regions reaches us, expanding the observable universe. But this expansion of the observable universe is slow compared to cosmic timescales. Each year, the observable radius increases by about 1 light-year, as light from 1 more light-year away reaches us. In the universe's lifetime of 13.8 billion years, this adds up to the current 46.5 billion light-year radius in proper distance. The CMB also reveals something remarkable about causality in cosmic horizons. The temperature variations we observe in the CMB show patterns on scales larger than could have been in causal contact at recombination. Regions of the CMB separated by more than about 2 degrees on the sky could not have exchanged information before recombination because light couldn't have travelled between them in the available time. Yet these regions have nearly identical temperatures, differing only by tiny amounts. How did they coordinate to have the same temperature if they couldn't communicate? This is the horizon problem, one of the puzzles that inflationary cosmology was invented to solve. Inflation posits an extremely rapid expansion in the universe's first fraction of a second. During inflation, regions that now separated by large distances were much closer and could have reached thermal equilibrium. Inflation then stretched them apart faster than light could travel between them. The CMB patterns we observe today thus contain imprints from an era before the observable universe was as large as it is now. When regions now separated were once in causal contact, future observations might detect neutrinos or gravitational waves from earlier epochs, potentially providing glimpses beyond the photon horizon. But for electromagnetic observation, The CMB is our ultimate boundary. The concept of the particle horizon formalizes what we mean by the edge of the observable universe and why that edge exists at a specific distance. The particle horizon is the maximum distance from which light or any signal could have reached us since the Big Bang. It defines the observable universe's boundary. This horizon exists because the universe has a finite age and light has a finite speed. Only regions close enough that light could traverse the distance in the universe's lifetime are observable. If the universe were infinitely old, there would be no particle horizon. Light from arbitrarily distant regions would have had time to reach us, but our universe is approximately 13.8 billion years old. This finite age, combined with light's finite speed and cosmic expansion, creates a definite horizon distance. The particle horizon distance is not simply the product of the universe's age and the speed of light. That would give about 13.8 billion light-years, ignoring expansion. Instead, we must integrate the distances light could have travelled in each era of the universe's expansion, accounting for how space was expanding at each time. In the early universe, space expanded rapidly, increasing distances faster than light travelled. This means light from a given region took longer to reach us than if space had been static. Conversely, once light is travelling toward us, the expansion of space behind it actually helps in a sense. The space between the light and more distant regions expands, but the light continues approaching us. The calculation requires integrating along the light's path, accounting for how the expansion rate changed as the universe evolved from radiation-dominated to matter-dominated to dark energy-dominated. The result of this integration, using measured cosmological parameters, gives a particle horizon distance of approximately 46.5 billion light-years. This is a proper distance, measured at the present cosmic time. It's how far away the most distant observable point is right now. Even though we see it as it was nearly 13.8 billion years ago, the particle horizon grows with time as light from ever more distant regions reaches us. It's not a fixed boundary, but an expanding sphere. Each moment the particle horizon increases slightly as we can see a bit farther, but the rate of increase is modest compared to cosmic timescales. Mathematically, the particle horizon distance at any time is the integral of the speed of light divided by the scale factor over cosmic time from the Big Bang to the present. The scale factor describes how distances in the universe have changed over time. It was very small in the early universe and has grown to its present value defined as 1. This integral can be evaluated using the Friedmann equations, which govern how the scale factor evolves based on the universe's energy content and geometry. For a flat universe dominated by matter and dark energy, the integral gives a particle horizon that's larger than the simple age times speed of light calculation by a factor of about 3.4. This factor comes from how expansion during the universe's history increased distances even as light was travelling. The particle horizon is a fundamental limit on observation. We cannot see beyond it with any electromagnetic radiation, regardless of technological advances. Improved telescopes can see fainter objects or resolve finer details within the observable universe, but they cannot see beyond the particle horizon. The only way to see farther is to wait. As time passes, light from more distant regions reaches us, expanding the observable universe. But this expansion is slow. In a human lifetime, the observable universe grows imperceptibly. Even over millions of years, the change is modest. There's also an interesting relationship between the particle horizon and causality. Regions beyond the particle horizon are causally disconnected from us. Events happening beyond the horizon now cannot affect us, and our actions cannot affect them. No signal or influence can travel faster than light, so communication is impossible. This means the observable universe is also the causally connected universe. At least in one direction. We can be affected by regions within the particle horizon but not beyond. However, we can affect regions beyond our current particle horizon if we wait long enough for signals to reach them. The causal future is larger than the observable past. The particle horizon thus represents both an observational and causal boundary, fundamental to understanding cosmic structure and what we can know about the universe. For practical cosmology, the particle horizon defines the scope of the field. We study the universe within this boundary, knowing that it continues beyond but accepting that the beyond is inaccessible. This limitation is sometimes philosophically troubling. How can we claim to understand, quote, zero if we can only observe a finite portion? The response is that we study the observable universe and extrapolate based on observed properties. If the observable universe appears homogeneous and isotropic, we assume this continues beyond the horizon. For understanding how far the observable universe extends, the particle horizon provides the answer. Approximately 46.5 billion light-years in proper distance, defined by the finite age of the universe, the speed of light, and the history of cosmic expansion. Let's work through the calculation that gives us the 93 billion light-year diameter more explicitly, understanding each factor that contributes to this remarkable number. The starting point is the universe's age, approximately 13.8 billion years, determined from multiple independent observations converging on this value. If light travelled through static space for 13.8 billion years, it would reach 13.8 billion light-years. Looking in all directions, we'd have an observable sphere 27.6 billion light-years across. But space is not static. It expands, and this expansion affects distances in crucial ways. When light was emitted from the most distant visible regions, the universe was much smaller. The cosmic scale factor was roughly 1/1000th its current value at the time of CMB emission. This means distances between all points in space were 1/1000th what they are now. The region that emitted the CMB we observe today was much closer to our location then than it is now. As the CMB photons travelled toward us, space expanded, stretching the distance between their emission point and us. This expansion carried the emission region farther away, even as light was approaching. By the time the CMB photons reach us now, the region that emitted them has been carried by expansion to approximately 46 billion light-years away in current proper distance. The mathematics involves integrating the expansion rate over cosmic history. The Friedmann equations describe how the scale factor changes with time based on the universe's energy content. The universe's energy budget has three main components: radiation, matter, and dark energy. Each contributes differently to expansion at different epochs. In the earliest times, radiation dominated. Radiation's energy density dilutes with the fourth power of the scale factor, because both the number density and energy per photon decrease. Matter, both ordinary and dark, dominated later. Matter density dilutes with the third power of the scale factor as volume increases but particle energies stay constant. Dark energy, which appears to be constant density per unit volume, doesn't dilute as space expands. This gives it increasing dominance as the universe expands. The transition from radiation to matter domination occurred about 50,000 years after the Big Bang. The transition from matter to dark energy domination occurred about 4 billion years ago. Each era has different expansion characteristics. Radiation domination causes rapid deceleration of expansion. Matter domination causes slower deceleration. Dark energy domination causes acceleration. The CMB was emitted during the matter-dominated era. Since then, the universe has transitioned to dark energy domination and begun accelerating. This complex expansion history determines how far the CMB emission region has been carried. The integration accounts for all these phases. The result, using measured cosmological parameters, gives approximately 46 billion light-years for the comoving distance to the surface of last scattering. The diameter is simply twice the radius, 93 billion light-years. This 93 billion light-year figure represents the current proper size of the observable universe, the diameter of the sphere within which we can observe electromagnetic radiation. Several observational confirmations support this calculated size. The CMB power spectrum, the pattern of temperature fluctuations at different angular scales, matches predictions based on this cosmology. The distances to supernovae, measured independently using their brightness, agree with the expansion history implied by these cosmological parameters. The abundance of light elements produced in Big Bang nucleosynthesis matches predictions from the same cosmological model. Large-scale structure observations, the distribution of galaxies across cosmic distances, fit the expected pattern from the same framework. All these independent observations converge on a consistent picture with specific parameter values that yield the 93 billion light-year observable universe size. Uncertainties in cosmological parameters create some uncertainty in the exact number. The age might be 13.7 or 13.9 billion years rather than exactly 13.8. The Hubble constant and dark energy density have measurement uncertainties that propagate into the distance calculation. But these uncertainties are relatively small, perhaps a few percent. The observable universe is definitely in the range of 90 to 95 billion light-years across, not radically different. Future observations will continue refining the parameters, sharpening the distance estimate, but the basic answer is well established. The 93 billion light-year diameter is sometimes described as the size of the observable universe, but more precisely it's the diameter of the region from which light has reached us. The universe itself might be much larger, possibly infinite. We can only observe the finite portion within our particle horizon. This distinction is important. When we say quote 1, we mean the observable portion, not necessarily the entire universe. Understanding why 93 billion light-years rather than 27.6 or any other number requires grasping cosmic expansion and how it affects light travel and distances. Once that framework is understood, the number follows from observation and calculation, revealing the majestic scale of the cosmic stage on which everything we observe unfolds. Understanding the observable universe's size requires understanding what we mean by cosmic expansion, a concept that's often misunderstood or described misleadingly. Cosmic expansion is not objects moving through pre-existing space. It's not galaxies flying apart like shrapnel from an explosion through a static void. Instead, space itself is expanding. The fabric of space grows, increasing distances between objects that aren't gravitationally bound to each other. This distinction is subtle but crucial. In the explosion analogy, galaxies would be moving through space with velocities they possessed from the initial explosion. But in cosmic expansion, galaxies can be essentially stationary with respect to their local space, while space itself expands between them. The standard analogy is raisins in rising bread dough. As the dough expands during baking, raisins move apart not because they're travelling through the dough, but because the dough between them is growing. Each raisin can be stationary relative to its immediate dough neighbourhood, while separating from distant raisins as the overall volume increases. For galaxies, this means they don't need to be quote 2 in the traditional sense to be receding from each other. The expansion of space carries them apart. This expansion is described by the scale factor, often denoted a t, which quantifies how distances change over cosmic time. If the scale factor doubles, all cosmic distances double. If it increases by a factor of 1,000, as it has since cosmic microwave background emission, distances have stretched by that factor. The expansion rate at any time is given by the Hubble parameter, h of t, which equals the time derivative of the scale factor divided by the scale factor. Today's Hubble parameter, the Hubble constant h0, is approximately 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, recession velocity increases by 67 kilometers per second. A galaxy 1 megaparsec away, about 3.3 million light-years, recedes at 67 kilometers per second. A galaxy 2 megaparsecs away recedes at 134 kilometers per second. This relationship, called Hubble's law, directly expresses cosmic expansion. Recession velocity is proportional to distance, exactly what space expansion predicts. If galaxies were just flying apart through static space from some initial explosion, there'd be no reason for this specific velocity-distance relationship. The expansion is uniform on large scales. Every region of space expands at the same rate, described by the same scale factor evolution. This means there's no center to the expansion. From any location, observers see the same pattern: distant galaxies receding with velocity proportional to distance. This is counterintuitive. We're used to explosions having centers, points from which material flies outward. But cosmic expansion has no center in three-dimensional space. The raisin bread analogy helps here too. As dough rises, every raisin sees other raisins receding, with more distant ones receding faster. No raisin is at the center. All positions are equivalent. For cosmology, this is expressed as the cosmological principle. The universe is homogeneous and isotropic on large scales. Every location and every direction is equivalent. Observations support this principle. The CMB looks the same in all directions after accounting for our motion. Galaxy distributions appear statistically identical in different regions. The expansion doesn't affect gravitationally bound systems. Earth's distance from the Sun doesn't increase. The Milky Way's size doesn't grow. Even galaxy clusters remain intact. Gravity's binding force overwhelms the cosmic expansion on these scales. Only on scales larger than galaxy clusters does expansion dominate. This is why we don't experience expansion locally. The expansion rate is tiny, about 7/100ths of a kilometre per second per megaparsec. Over the Earth-Sun distance of about 1 astronomical unit, this translates to expansion of less than 1 millimetre per century, completely negligible compared to gravitational and other forces. The expansion is only significant over cosmological distances, millions or billions of light years, where the cumulative effect becomes substantial. One profound consequence: expansion can carry distant galaxies away faster than light. There's no speed limit on how fast space itself can expand. Special relativity limits the speed of objects moving through space. But it doesn't limit how fast space can grow, carrying objects with it. This is possible because the Hubble parameter has been decreasing over most of cosmic history in absolute terms, though the expansion has been accelerating in recent billions of years due to dark energy. Understanding cosmic expansion as space itself, growing rather than motion through space, is essential for making sense of the observable universe's size and properties. It explains why the universe can be 93 billion light-years across when only 13.8 billion years old. The expansion stretched distances beyond what simple light travel predicts. It explains why recession velocities can exceed light speed without violating relativity. It explains the velocity-distance relationship and why every location appears equivalent. Cosmic expansion is thus the key framework for understanding cosmic distances, the observable universe's extent, and how that extent relates to the universe's age and properties. Related to but distinct from the particle horizon are two other cosmic boundaries, the Hubble sphere and the event horizon, each defining different limits on observation and causality. The Hubble sphere is the distance at which the recession velocity from cosmic expansion equals the speed of light. This occurs at a distance equal to the speed of light divided by the Hubble constant. With the current Hubble constant of about 67 kilometers per second per megaparsec, the Hubble sphere radius is approximately 14 billion light-years in proper distance. This is an instantaneous concept defining which regions are currently receding faster than light versus slower than light. Regions within the Hubble sphere are receding slower than light. Regions beyond are receding faster than light. The Hubble sphere is the boundary between these regimes. The Hubble sphere is not the same as the particle horizon. The particle horizon, at 46 billion light-years, is much larger than the Hubble sphere. This means many regions we can observe are currently receding faster than light. We see them because light they emitted in the past, when they were within the Hubble sphere, has reached us. The Hubble sphere is also not fixed. As the expansion rate changes, the Hubble sphere grows or shrinks. In the early universe with rapid expansion, the Hubble sphere was much smaller. As expansion decelerated during the matter-dominated era, the Hubble sphere grew. This growth allowed light from distant regions to enter the Hubble sphere and eventually reach us. Without this Hubble sphere growth, light from beyond the early Hubble sphere could never reach us, because it would be carried away faster than it could approach. The physical interpretation is subtle. Light emitted from beyond the Hubble sphere initially moves away from us in terms of proper distance, because space between us and the photon expands faster than light travels through space. But if the photon is travelling toward us through its local space, it eventually enters regions where expansion is slower. If the Hubble sphere is growing, the photon can enter it. Once in the Hubble sphere, where recession velocity is less than light speed, the photon makes net progress toward us in proper distance and eventually arrives. Regions beyond the event horizon are forever unobservable. They're beyond our causal future as well as our observable past. This creates a profound limitation. Dark energy-driven acceleration means the observable universe will not continue growing indefinitely, but will asymptotically approach a maximum size. Eventually, light from beyond the current event horizon will be unable to reach us, because expansion accelerates those regions away faster than light can approach. The event horizon thus represents the ultimate limit of observation in an accelerating universe. The particle horizon will approach, but never exceed the event horizon as time goes to infinity. Currently, the particle horizon is larger than the event horizon, because we're observing light emitted in the past when those regions were much closer. But future light from those regions won't reach us. We're seeing their past, but not their future. This seems paradoxical. How can we see a region's past, but not its future? The answer lies in when the light was emitted versus when it will arrive. Light emitted from near the event horizon in the distant past had time to reach us, because the universe wasn't expanding as fast then, and the light had billions of years to travel. But light emitted from the same region now will never reach us because acceleration carries it away faster than it can approach. The relationships between these horizons are complex. The particle horizon tells us how far we can currently see. The Hubble sphere tells us which regions are currently receding faster than light. The event horizon tells us how far we'll ever be able to see. In our universe, particle horizon greater than Hubble sphere greater than event horizon currently. But these relationships change over time. All three horizons are growing, but at different rates. The particle horizon grows fastest. The event horizon grows slowest and will eventually stop growing. These different horizons highlight how cosmic expansion creates multiple boundaries relevant to different questions about observability and causality. For understanding how far the observable universe reaches now, the particle horizon is most relevant. That's the 46 billion light-year radius we've been discussing. But the Hubble sphere helps understand why we can see galaxies receding faster than light, and the event horizon reveals future limitations on observation. Together, these concepts paint a rich picture of cosmic boundaries, showing how the finite age and accelerating expansion create multiple scales beyond which different types of observation become impossible. Understanding these horizons is essential for grasping the full complexity of how far the observable universe extends and what that means for cosmology and our cosmic future. Determining how far the observable universe extends requires knowing how fast space is expanding, encoded in the Hubble constant and its evolution over cosmic time. The Hubble constant, denoted h0, is the current expansion rate. It tells us how quickly distances are increasing right now per unit distance. Edwin Hubble's original measurement in 1929 gave about 500 kilometers per second per megaparsec, roughly 7 times higher than modern values. This was based on distance measurements to nearby galaxies using Cepheid variables and their recession velocities from Doppler shifts. Hubble's distances were systematically wrong, because he didn't properly distinguish between different types of variable stars, leading to incorrect distance calibrations. Knowing both the current h0 and the evolution h of t allows calculating distances to any redshift and determining the particle horizon distance. These measurements come from combining multiple observations, supernova distances, CMB power spectrum, baryon acoustic oscillations in galaxy distributions, and more. The concordance emerges from these diverse observations, all pointing to consistent cosmological parameters, giving confidence in the framework despite the Hubble tension. The expansion rates measurement is thus central to determining how far the observable universe extends. Different expansion histories give different horizon distances. Current measurements indicate expansion has been slowing throughout most of cosmic history, but began accelerating recently due to dark energy. This specific history, combined with the universe's age, produces the 46.5 billion light-year particle horizon radius. If expansion had always been decelerating, the particle horizon would be somewhat smaller. If acceleration began earlier, it would be larger. The precise measurements of expansion history thus pin down the observable universe's size to good accuracy, despite remaining puzzles like the Hubble tension. Future observations, from improved supernova measurements to next-generation CMB observations to gravitational wave standard sirens, will continue refining these measurements. The goal is to resolve the Hubble tension and determine h0 to 1% or better accuracy, which would sharpen our knowledge of cosmic distances proportionally. For now, we know the expansion rate well enough to say with confidence that the observable universe is roughly 93 billion light-years across, with uncertainties of perhaps a few percent. Dark energy plays a crucial role in determining the observable universe's size and particularly its future evolution, affecting both what we can observe and how far that extends. Dark energy is the mysterious component causing the universe's expansion to accelerate. It comprises about 68% of the universe's total energy density. Its nature remains one of physics' biggest mysteries. The simplest explanation is vacuum energy, a constant energy density intrinsic to space itself. This energy doesn't dilute as space expands. If space has constant energy density per unit volume, then as volume increases, total dark energy increases proportionally. This creates a repulsive gravitational effect, causing accelerated expansion. The more space exists, the more dark energy, driving faster expansion. The cosmological constant, denoted lambda, represents this constant vacuum energy in Einstein's equations. It's the simplest dark energy model and fits observations well. Alternative models allow dark energy density to vary with time, called quintessence or other exotic names. But observations so far are consistent with constant lambda. Dark energy's effect on cosmic distances is profound. Without it, expansion would continue decelerating forever, gradually slowing due to matter's gravitational attraction. With dark energy dominating, expansion accelerates exponentially in the far future. This drastically changes the long-term fate of the observable universe. For past expansion history, dark energy was negligible. When the universe was young and dense, matter and radiation dominated. Dark energy only became important when the universe expanded enough that matter density dropped below dark energy's constant density. This transition occurred about 4 billion years ago. Before then, expansion was decelerating. Since then, it's been accelerating. This transition affects how the particle horizon has grown over time. When expansion was decelerating, the Hubble sphere grew rapidly, allowing light from very distant regions to enter and eventually reach us. With accelerating expansion, the Hubble sphere growth has slowed and will eventually stop. This limits how much farther we'll ever be able to see. The event horizon, the maximum distance we'll ever observe, is determined primarily by dark energy. If dark energy is constant, exponential expansion in the far future prevents light from beyond about 16 billion light-years from ever reaching us. Regions within this event horizon can eventually be observed given enough time. Regions beyond cannot, no matter how long we wait. This creates a cosmic horizon in the future similar to the particle horizon from the past, but for different reasons. Dark energy also affects the observable universe's current size calculation. The particle horizon integral includes the dark energy contribution to expansion over the past few billion years. Without dark energy, the universe would be slightly older for the same current expansion rate, and the particle horizon would be slightly different. The precise mix of matter and dark energy affects the integral's value, though the effect is modest for the current epoch. For distant galaxies, dark energy affects the relationship between redshift and distance. At high redshifts before dark energy dominated, distances follow one relation. At low redshifts after dark energy took over, they follow another. This creates subtle features in distance redshift relations that observations can detect, providing evidence for dark energy's existence and properties. The supernova observations that discovered accelerating expansion worked precisely by measuring this distance redshift relation at intermediate redshifts, where dark energy's effects became apparent. Supernovae farther than expected for a decelerating universe indicated acceleration, revealing dark energy. Dark energy's influence grows stronger with time. Currently, it dominates the energy budget at about 68%. In the far future, its percentage will approach 100 as matter dilutes to negligibility. This future evolution has profound implications. Galaxies beyond the local group will accelerate away from us, eventually receding faster than light and disappearing beyond our event horizon. The observable universe, instead of continuing to grow as it has throughout cosmic history, will eventually shrink as distant objects cross our event horizon. Billions of years from now, only gravitationally bound structures like the local group will remain observable. The rest of the universe will have receded beyond reach. This cosmic isolation is dark energy's long-term consequence, creating a lonely future where most of the current observable universe becomes unobservable. For the present, dark energy's role is to accelerate expansion modestly, affecting distance measurements at large redshifts and determining where the event horizon lies. Understanding dark energy is thus crucial for understanding not just how far we can see now, but how far we'll ever be able to see. The observable universe's 93 billion light-year extent represents a nearly maximal value in some sense. Future accelerated expansion will make this the approximate size of everything we'll ever observe. New regions will become observable for a while as light from slightly beyond the current particle horizon reaches us. But this growth will slow and eventually reverse as dark energy's acceleration intensifies. The far future observable universe might contain only the local group merger remnant, isolated in expanding space, with the CMB redshifted to undetectability. This cosmic future scenario depends on dark energy remaining constant or strengthening. If dark energy weakens or disappears, the future would be different. Current observations suggest dark energy is constant within measurement precision. But long-term behavior remains uncertain. For our current question of how far the observable universe extends, dark energy's role is to have modestly accelerated expansion over the past few billion years, and to set the event horizon that limits future observation. The 93 billion light-year scale thus represents the extent of everything we can currently observe, and most of what we'll ever observe, with dark energy ensuring that future observations won't dramatically exceed this scale. Having explored how far we can observe, it's worth contemplating what lies beyond the observable universe, acknowledging both what we can infer and what remains fundamentally unknowable. The most straightforward expectation is that the universe continues beyond our observable horizon, with properties similar to what we observe within it. The cosmological principle suggests the universe is homogeneous and isotropic on large scales. If this holds beyond the observable region, Space continues with galaxies, clusters, and large-scale structure like what we see. This isn't merely speculation. The observable universe's properties, particularly the CMB's uniformity, suggest that homogeneity extends well beyond what we can directly observe. The CMB shows regions that were causally disconnected at recombination, yet have nearly identical properties. This suggests underlying homogeneity on scales larger than causal horizons. Inflation theory provides a mechanism for creating this large-scale homogeneity. During inflation's brief moment, the universe expanded by enormous factors. A tiny causally connected region was inflated to sizes vastly larger than the current observable universe. Different parts of what we see were once close enough to reach thermal equilibrium. After inflation ended, these regions were separated by distances larger than light could have travelled since then, creating the observable universe's horizons. If this picture is correct, the universe beyond our horizon should look statistically similar to our observable region, because it originated from the same inflated patch. The total size of the inflated region depends on inflation's details, but many models predict it's vastly larger than the observable universe, perhaps by factors of 10 to the 30 power or more. This would make the observable universe a tiny fraction of the total universe, like a single atom in a planet-sized object. Some would be similar to ours, with minor variations. Others would differ dramatically. All possibilities would be represented somewhere in the infinite expanse. This philosophical speculation is untestable. We can never observe beyond our particle horizon to verify or refute these ideas about the distant universe. Alternative possibilities exist. The universe beyond our horizon might be drastically different if the cosmological principle breaks down at super-horizon scales. Perhaps properties we consider fundamental, like the values of physical constants or even the number of spatial dimensions, vary across super-horizon distances. Some multiverse theories propose this kind of variation. Different regions might have different physics, with only some regions suitable for complex structures and life. We would necessarily find ourselves in a suitable region, an observational selection effect. But other regions with different properties might exist beyond observation. These speculations are creative and interesting but lack empirical support. We have no evidence that properties vary beyond our horizon. The most conservative interpretation is that the universe continues beyond our horizon much as it appears within, with similar properties extending for potentially infinite distances. This doesn't answer whether the universe is infinite or finite but very large. A spatially flat universe, which observations support, could be either infinite or finite with special topology. If finite, the universe might have a topology like a 3 torus, where travelling far enough in one direction brings you back from the opposite direction, like the surface of a video game screen. Observations constrain how small such a universe could be. If smaller than the observable universe, we might see the same galaxies in multiple directions, creating distinctive patterns. No such patterns are observed, suggesting that if the universe is finite, it's larger than the observable region by at least a modest factor. The question of what lies beyond the observable universe thus has no definitive answer from observation. We can infer, theorize, and speculate, but we cannot directly verify. This limitation is fundamental. The finite speed of light and finite age of the universe create an insurmountable observational boundary. Even perfect future instruments cannot see beyond the event horizon. The unobservable region remains forever beyond empirical science's reach. This might seem frustrating, but it's also philosophically interesting. It reminds us that some questions lie beyond science's scope, not due to technological limitations, but due to fundamental constraints. For understanding the observable universe itself, what lies beyond is largely irrelevant. We study what we can observe and build models consistent with those observations. Whether the universe is infinite or finite but large, whether it's similar or different beyond our horizon, doesn't affect our ability to understand the observable portion. The 93 billion light-year observable region is vast enough to contain hundreds of billions of galaxies and rich enough in structure to keep astronomers busy for centuries. What lies beyond remains a source of wonder and speculation, perhaps forever beyond definitive knowledge, but endlessly fascinating to contemplate. Determining how far the observable universe extends requires accurately measuring cosmic distances, which has driven development of increasingly sophisticated techniques over the past century. The cosmic distance ladder is a series of methods, each calibrated by the previous and reaching farther into space, eventually extending to cosmological distances. The first rung is geometric methods like parallax. As Earth orbits the Sun, nearby stars appear to shift position against more distant background stars. Measuring this parallax angle gives direct geometric distance through simple trigonometry, requiring no assumptions about the star's properties. Ground-based parallax worked for stars within about 100 light-years. The Hipparcos satellite extended this to roughly 300 light-years. The Gaia mission has revolutionized parallax measurements, providing accurate distances to stars throughout much of the Milky Way, out to tens of thousands of light-years for bright stars. Gaia's data calibrates the next distance ladder rungs by measuring properties of nearby standard candles whose distances are known from parallax. Cepheid variable stars remain crucial to the distance ladder. Their period luminosity relation, discovered by Henrietta Leavitt, allows using pulsation period to determine absolute brightness. Comparing absolute brightness to observed apparent brightness gives distance through the distance modulus formula. Gaia has measured parallaxes for Cepheids in the Milky Way, calibrating their period luminosity relation to high precision. These nearby Cepheids calibrate more distant Cepheids observable in other galaxies, extending distance measurements to tens of millions of light-years. The Hubble Space Telescope has observed Cepheids in galaxies throughout the local universe, measuring distances to galaxies as far as 100 million light-years or more. For even greater distances, other methods are needed. The CMB provides distance information through its physics. The CMB power spectrum, the pattern of temperature fluctuations at different angular scales, depends on cosmological parameters including distances. The sound horizon at recombination, how far sound waves travelled in the early universe's plasma, creates a characteristic angular scale in the CMB. Measuring this angular scale determines the distance to the surface of last scattering, about 46 billion light-years in proper distance. This doesn't depend on previous ladder rungs but uses fundamental physics, making it an independent distance measurement. Baryon acoustic oscillations, the same sound waves imprinted in the CMB but later frozen into galaxy distributions, provide another standard ruler. The characteristic length scale of about 500 million light-years appears in galaxy clustering statistics. Measuring this scale's apparent angular size at different redshifts gives distances. BAO measurements work to redshifts beyond 1, overlapping with and extending supernova measurements. Gravitational lensing provides another distance probe. When light from distant quasars passes near massive galaxies, it's bent and often creates multiple images. Time delays between images arriving depends on the distances to the lens and source. Measuring these delays determines distances to cosmological objects. This technique is developing and promises to provide independent distance measurements complementary to other methods. Each distance measurement method has systematics and uncertainties. Combining multiple methods provides cross-checks and improves overall reliability. The cosmic distance ladders. Power comes from this multiple method approach. Distances determined from Cepheids, supernovae, CMB, and BAO all converge on consistent values. This convergence gives confidence that the framework is correct, even where individual measurements have uncertainties. The Hubble constant measurement relies on this ladder. Measuring supernovae distances and redshifts determines H0 by comparing recession velocities to distances. The The Hubble tension arises because distance ladder-based measurements give slightly different H0 than CMB-based determinations. Resolving this tension requires either finding systematic errors in measurements or understanding if the discrepancy indicates new physics. Current research focuses on improving each ladder rung's calibration, searching for systematics, and developing new independent methods. Gravitational wave detections of binary neutron star mergers, which produce both gravitational waves and electromagnetic signals, provide a promising new distance measurement. The gravitational wave signals' properties determine luminosity distance directly, without needing calibration from other methods, making them independent standard sirens. As more such events are detected, they'll provide additional constraints on H0 and cosmic distances. For our question of how far the observable universe extends, these distance measurements determine the expansion history needed to calculate the particle horizon. The combination of local H0 measurements, supernova distances, CMB observations, and BAO measurements all feed into the cosmological model. That model's parameters, once determined, allow calculating the particle horizon distance. Approximately 46.5 billion light-years. This number depends on the accuracy of distance measurements. As measurements improve, the number's precision increases, though the value doesn't change dramatically. The cosmic distance ladder thus provides the observational foundation for determining how far we can see, connecting local measurements to cosmological scales. The cosmic microwave background provides the most direct measurement of the observable universe's size because it comes from the particle horizon itself, the farthest we can observe. The CMB was predicted theoretically in the 1940s as a consequence of Big Bang cosmology. A hot, dense early universe would have emitted thermal radiation, cooled by expansion to microwave wavelengths by now. The accidental discovery in 1965 by Penzias and Wilson confirmed this prediction. Providing strong evidence for the Big Bang model, early measurements determined the CMB's average temperature, about 2.7 Kelvin, remarkably uniform across the sky. This uniformity was puzzling. How could regions of the universe causally disconnected at recombination have identical temperatures? The horizon problem motivated inflationary cosmology. Inflation would have brought distant regions into thermal contact before expansion separated them beyond causal reach. But perfect uniformity would also be problematic. If the early universe were perfectly smooth, structure formation theory predicts no galaxies would form. Tiny density variations were needed to seed galaxy formation through gravitational collapse. These variations should appear as temperature variations in the CMB. In 1992, the COBE satellite detected these variations for the first time, temperature fluctuations of about 1 part in 100,000. The power spectrum has a characteristic shape with multiple peaks and troughs. Each feature encodes information about cosmological parameters. The first peak's location depends on the sound horizon's angular size, which determines the distance to the surface of last scattering. This distance measurement is extraordinarily precise. Planck determined it to about 0.5% accuracy. From this measurement and knowing the redshift of the CMB, about 1090, cosmologists calculate the particle horizon distance, 46 billion light-years in proper distance. The CMB thus directly measures the observable universe's size through first principles physics rather than distance ladder calibrations. This makes it particularly robust and independent of local measurements, though the Hubble tension shows some disagreement between CMB and local measurements. The CMB power spectrum also determines the universe's spatial curvature. Observations show space is flat to within about 1%. A flat universe means parallel lines remain parallel over cosmic distances. It's one of 3 possible geometries, along with positive curvature, like a sphere, and negative curvature, like a saddle. Curvature affects observable universe calculations. A positively curved universe might be finite and smaller than calculated for flat geometry. Negative curvature would make calculations slightly different. But with curvature this close to zero, the flat space calculation is effectively correct for determining the observable universe's size. The CMB observations also constrain the universe's matter content. The relative heights of different power spectrum peaks depend on the ratio of ordinary matter to dark matter. Planck's measurements determine this ratio precisely, finding about 84% dark matter, 16% ordinary matter in the matter budget. The total matter fraction relative to dark energy determines expansion history, which feeds into calculating the particle horizon distance. All these parameters from CMB observations combine to give a precise model of cosmic expansion history from recombination to present. Integrating this expansion history gives the particle horizon distance with about 3% uncertainty, including all parameter uncertainties. Future CMB observations from ground-based telescopes like the Simons Observatory and CMB-S4 will measure polarization patterns with higher precision. These measurements will refine cosmological parameters further, potentially resolving current tensions and sharpening our knowledge of the observable universe's extent. The CMB thus serves multiple roles. It's the farthest thing we observe, it defines the observable universe's boundary, and its detailed properties determine that boundary's distance. Understanding the CMB is therefore essential for answering how far the observable universe reaches. The answer comes directly from analysing the CMB's properties and the physics of the surface of loss scattering. Beyond measuring the CMB, observations of large-scale structure throughout the observable universe provide complementary information about cosmic distances and the universe's extent. Large-scale structure refers to how galaxies are distributed across cosmic volumes, forming clusters, filaments, sheets, and voids, creating a cosmic web. This structure arose from gravitational growth of tiny density variations present in the early universe, visible as CMB temperature fluctuations. Over billions of years, overdense regions attracted more matter and grew denser, while underdense regions emptied out, creating the web structure we observe. Mapping this structure requires surveying millions of galaxies, measuring their positions and distances to construct three-dimensional maps. The Sloan Digital Sky Survey, beginning in 2000, was a pioneering large-scale survey mapping millions of galaxies across significant cosmic volume. SDSS measured distances through spectroscopic redshifts, determining each galaxy's recession velocity and using Hubble's law to convert velocity to distance. The resulting maps showed cosmic structure across billions of light-years, revealing filaments, voids, and the web's overall statistical properties. Subsequent surveys like 2DFGRS, BOSS, EBOSS, and ongoing programs like DESI continue expanding these maps, surveying larger volumes and reaching higher redshifts. These surveys measure baryon acoustic oscillations. The characteristic 500 million light-year scale imprinted by sound waves in the early universe. Bohr appears as a small excess in the probability of finding pairs of galaxies separated by about 500 million light-years compared to slightly larger or smaller separations. Measuring this scale's apparent angular size at different redshifts constrains the expansion history and distances, providing a standard ruler across cosmic time. BAO measurements from galaxy surveys agree remarkably well with CMB measurements, confirming the cosmological model's consistency across different observational approaches. The surveys also measure the growth rate of structure over cosmic time. How quickly density variations amplify depends on gravity strength and dark energy's properties. Comparing structure at different epochs tests whether gravity behaves as general relativity predicts on cosmic scales and provides independent dark energy constraints. These measurements all feed into determining cosmological parameters that specify the expansion history and thus the observable universe's size. The James Webb Space Telescope is designed to observe even earlier galaxies, potentially reaching redshifts of 20 or beyond, seeing galaxies just 100 or 200 million years after the Big Bang. These observations probe the observable universe's extent in the sense of observing objects at large distances, even if not quite reaching the CMB surface. Each detected galaxy at high redshift confirms that the universe at that location and epoch had properties similar to the local universe, supporting the cosmological principle's extrapolation. Large-scale structure observations also test inflation's predictions. Inflation predicts a particular pattern of density fluctuations, characterized by an almost scale-invariant power spectrum. Measuring how structure's amplitude varies with scale tests this prediction. Observations match inflationary expectations well, supporting the framework. If large-scale structure observations found significant deviations from predictions, it might indicate the universe beyond the observable region differs from what we see. But no such deviations are observed. Structure across the observable volume appears statistically homogeneous and consistent with simple models. This gives confidence that the universe continues beyond our horizon with similar properties, supporting the assumption that the observable universe's size calculations apply to understanding the larger universe. Future surveys like Euclid and the Roman Space Telescope will map larger cosmic volumes with better precision, continuing to test cosmological models and refine parameter determinations. These measurements will incrementally improve our knowledge of the observable universe's size and properties, though dramatic changes are unlikely given how well current observations already constrain the framework. Large-scale structure observations thus complement CMB measurements, providing multiple independent probes of cosmic expansion and distances. Together, these observations converge on the 46 billion light-year particle horizon distance, confirming the observable universe's 93 billion light-year diameter. One of the most profound aspects of observing the distant universe is that we're not just seeing faraway places but also looking backward in time, observing cosmic history directly. Light travels at a finite speed, about 300,000 kilometers per second. This means light takes time to traverse cosmic distances. Light from the Moon takes about 1.3 seconds to reach Earth. We see the Moon as it was 1.3 seconds ago. Sunlight takes about 8 minutes to reach us. We see the Sun as it was 8 minutes ago. If the Sun suddenly disappeared, we wouldn't know for 8 minutes. This light travel time becomes significant at astronomical distances. The nearest star, Proxima Centauri, is about 4.2 light-years away. We see it as it was 4.2 years ago. Any event happening there now won't be visible from Earth for over 4 years. For the Andromeda Galaxy, about 2.5 million light-years away, we see light that left before modern humans evolved on Earth. The CMB shows us the universe at age 380,000 years, almost at the very beginning. Beyond the CMB, we cannot look further back in time with electromagnetic radiation, because the universe was opaque earlier. Neutrinos from the early universe, if we could detect them, would show even earlier times. Gravitational waves from inflation would reveal the first fractions of a second, but photons only allow seeing back to recombination. The CMB is our earliest view with light. This creates an interesting relationship between distance and time. Greater distance means earlier cosmic epoch. The particle horizon's distance of 46 billion light-years in proper distance corresponds to seeing back to nearly the Big Bang itself. We can plot cosmic history by look-back time. Zero look-back time is here and now. Maximum look-back time is 13.8 billion years at the CMB. Different cosmic epochs occupy different look-back time ranges. Recombination at 380,000 years. First stars at perhaps 100 to 200 million years. First galaxies at 4. 100 million years. Our Sun and Solar System formed at look-back time 9 billion years, about 4.6 billion years ago. Humanity evolved at effectively zero look-back time on cosmic scales, just a few 100,000 years ago out of billions. When we observe the distant universe, we're reconstructing cosmic history through spatial surveys. Each galaxy's redshift places it in cosmic time. By surveying galaxies at many redshifts, we map the universe's evolution from early epochs to recent times, seeing how structure developed and galaxies evolved. This is cosmic archaeology, piecing together history from observations at different times rather than watching evolution happen. The limit is the CMB surface at the particle horizon. We can observe cosmic history from 380,000 years after the Big Bang to now, but not earlier with photons. This creates a practical limit on how far back in time we can see, corresponding to the limit on how far away we can observe. The observable universe's spatial extent thus equals its temporal depth. 93 billion light-years across corresponds to seeing 13.8 billion years into the past from all directions. This unity of space and time is characteristic of relativity. Cosmic distances are also cosmic times, with events at large distances being in the distant past. Looking outward into the universe is looking backward into history, and the farthest view is the earliest view, showing us the cosmos as it was just beginning. While we focused on how far the observable universe currently extends, it's worth considering how this distance will change over time and what the distant future holds. The observable universe is not static. The particle horizon expands as light from ever more distant regions reaches us. Each moment, we can see slightly farther as light that was previously beyond reach completes its journey to us. In a decelerating universe, the particle horizon would grow without limit. Eventually, light from arbitrarily distant regions would arrive, making the entire universe observable given enough time. But our universe is accelerating due to dark energy. This changes the future dramatically. Accelerating expansion means the Hubble sphere grows slower than in a decelerating universe. Eventually it will stop growing if acceleration continues. The event horizon, the maximum distance we'll ever observe, is set by this future expansion behavior. For a cosmological, constant driving, eternal exponential expansion, the event horizon stabilizes at about 16 billion light-years in proper distance. Light emitted now from beyond this event horizon will never reach us. Accelerating expansion carries those regions away faster than light can close the distance. Currently, the particle horizon at 46 billion light-years is larger than the event horizon. We're observing light emitted in the distant past from regions now beyond our future reach, but we can still observe more distant regions in the future as their ancient light arrives. The particle horizon will continue growing, approaching but never exceeding the event horizon. Asymptotically, billions of years from now, the particle horizon will reach about 16 billion light-years and stop growing as it matches the event horizon. At that point, the observable universe stops expanding. No additional regions become observable because light from beyond the event horizon can never arrive. Meanwhile, galaxies beyond our local gravitationally bound group are accelerating away. Eventually they'll cross the event horizon and disappear. Their light will become increasingly redshifted as they accelerate away. Eventually the redshift becomes infinite and they fade from view. Calculation suggests that in perhaps 100 billion years, only the local group and its merger remnant with Andromeda will remain observable. All other galaxies will have receded beyond the event horizon, disappearing from view as their light redshifts to infinity. This CMB itself will redshift to undetectable wavelengths, becoming invisible to even the most sensitive instruments. Future observers in this distant epoch would see only their local galaxy in an otherwise empty, dark universe. They would have no observational evidence for cosmic expansion, the Big Bang, or the existence of other galaxies. All the cosmology we've learned would be unobservable to them. The universe's history and contents would be hidden by accelerating expansion. This scenario highlights how fortunate we are to live in an epoch where cosmology is possible. We can observe the CMB, distant galaxies, and measure expansion. Our current epoch, with observable evidence for the Big Bang and cosmic expansion visible in the sky, is special and temporary. Before galaxies formed, there was nothing to see but primordial plasma. After distant galaxies recede beyond reach, there will be nothing to see but our local group. Only during this cosmological moment, lasting perhaps tens of billions of years, can observers measure the universe's full properties. This has philosophical implications. It suggests our existence in this observable epoch might not be coincidental, but related to conditions necessary for life. Complex chemistry requires heavy elements from stellar nucleosynthesis. Life requires stable stellar systems and planets. These conditions might correlate with observable epochs. For the practical question of how far the observable universe extends in the future, the answer is not much farther than now. The particle horizon will grow from 46 billion light-years toward the event horizon at 16 billion, an increase of less than a factor of 2. Most of the observable universe's eventual extent is already observable now. Future centuries will see incremental additions but not dramatic expansions. This is very different from the past. Throughout cosmic history, the observable universe has grown rapidly as the Hubble sphere expanded faster than the universe itself. The transition from growing observability to shrinking observability occurred recently on cosmic timescales as dark energy became dominant. Current observations are consistent with constant dark energy, but long-term behavior remains uncertain. Future observations might reveal evolution in dark energy properties. For now, we can say with confidence that the observable universe will not grow dramatically from its current 93 billion light-year extent. The far future observable universe will be somewhat larger, perhaps 100 billion light-years, but not vastly different from today. Most of the cosmos we'll ever observe is already within our particle horizon, visible to sufficiently powerful telescopes. The observable universe's size is thus approaching its maximum, limited not by technological capabilities, but by the fundamental physics of accelerating expansion. A crucial distinction for understanding cosmic extent is separating the observable universe from the actual universe, recognizing that what we can see may be a tiny fraction of what exists. The observable universe is definitionally the region from which light has reached us. Its 93 billion light-year diameter represents our observational horizon. But this horizon is a property of observation, not necessarily a boundary of existence. Space likely continues beyond what we can observe. Several lines of reasoning suggest the universe beyond our horizon exists and contains matter and structure similar to what we observe. First, there's no physical reason to expect space ends at our observational boundary. The particle horizon is determined by light travel time, not by any physical edge. In the past, our particle horizon was smaller. Regions now within the observable universe were once beyond it. As time passed and light from those regions arrived, they became observable. This suggests regions currently beyond our horizon are real, and will eventually become observable, given enough time in a non-accelerating universe. Second, the cosmological principle, supported by observations showing homogeneity and isotropy, suggests the universe has similar properties everywhere. If the observable universe appears homogeneous on large scales, parsimony suggests this homogeneity continues beyond what we observe. There's no evidence for edges or special boundaries at the observable universe's limit. Properties appear consistent with continuation of similar structure. Third, inflation theory predicts the universe is vastly larger than the observable region, possibly infinite. During inflation's brief moment, the universe expanded by enormous factors, perhaps 10 to the 30 power or more. A tiny region became larger than the current observable universe. The observable universe would then be just one small patch of a much larger inflated region, all of which underwent the same physics. If inflation occurred, the universe beyond our horizon should look statistically similar to our observable region, because they share a common origin. Some estimates suggest the universe might be at least 10 to the 23rd power, times larger than the observable region in volume, possibly infinite. These numbers are speculative and model-dependent. but they illustrate that the observable universe might be cosmically insignificant in extent. An analogy: imagine being in the middle of an ocean, able to see to the horizon perhaps 5 kilometers away. The visible ocean is your observable ocean, but the ocean continues well beyond your horizon. Your observational limit doesn't define where water ends. Similarly, our cosmic horizon doesn't define where space ends, just where our observations reach. The key question is whether the actual universe is finite or infinite. Observations provide some constraints, but no definitive answer. Spatial curvature measurements show the universe is very close to flat. A perfectly flat universe could be infinite, or could have special topology making it finite but unbounded. If truly infinite, the universe contains infinite matter and infinite galaxies extending forever beyond any horizon. An infinite universe raises conceptual challenges. It would contain infinite copies of any finite region, including infinitely many identical copies of our observable universe. This seems philosophically troubling, but isn't logically inconsistent. Infinity allows for such repetitions. Alternatively, the universe might be finite but very large, perhaps thousands or millions of times the observable volume. A finite universe could have topology like a 3 torus, where travelling far enough brings you back to the starting point. Like Pac-Man wrapping around screen edges, current observations constrain how small such a universe could be. If smaller than the observable region, we might see the same structures in multiple directions. This uncertainty is sometimes presented as a limitation of cosmology. How can we claim to understand, quote, 4 if most of it might be unobservable? The response is that cosmology studies the observable universe, using its properties to infer likely properties of the larger whole based on homogeneity. If the unobservable universe is similar to the observable portion, which seems likely, then understanding the observable universe is understanding a representative sample. If the unobservable universe is different, we might never know, but absent evidence for differences. Assuming similarity is reasonable, the observable versus actual distinction thus highlights both the power and limitations of cosmological observation. We can measure properties within our horizon precisely, and infer that similar properties extend beyond. But we cannot directly verify those inferences. The 93 billion light-year observable universe is what science can study empirically. Beyond lies inference, theory, and philosophy. Interesting, but not empirically accessible. The observable universe's extent encodes information about cosmic history, revealing how the universe evolved from the Big Bang to the present through the specific distance we measure. The 46 billion light-year particle horizon distance results from integrating expansion history over 13.8 billion years. Different expansion histories would give different particle horizon distances. The specific value we observe reveals what actually happened. Early in cosmic history, the universe was radiation-dominated. Photons and other relativistic particles contributed most of the energy density. Radiation domination causes rapid deceleration of expansion. The Hubble parameter was very large, and the Hubble sphere was very small. During this era, the particle horizon grew slowly compared to the overall size of the universe. Much of space was beyond any given location's horizon. This is related to the horizon problem inflation solves. Without inflation, causally disconnected regions at recombination couldn't have reached thermal equilibrium. As the universe expanded and cooled, radiation density decreased faster than matter density. Eventually, matter became dominant about 50,000 years after the Big Bang. During matter domination, expansion decelerated more slowly than during radiation domination. The Hubble sphere began growing faster. This allowed light from distant regions to enter the Hubble sphere and eventually reach observers. The particle horizon expanded rapidly. Most of the observable universe's current extent comes from this matter-dominated era, when expansion decelerated and the Hubble sphere grew quickly. The CMB surface became observable because regions that emitted it were initially beyond the Hubble sphere, but the Hubble sphere grew to encompass them. About 4 billion years ago, another transition occurred. Dark energy became dominant over matter, causing expansion to begin accelerating. Accelerating expansion slows the Hubble sphere's growth. In the far future, it will stop growing entirely if acceleration continues. This transition to dark energy domination determines the event horizon's location and ensures the observable universe won't grow much larger. The factor of 3.4 by which proper distance exceeds light travel time reflects the specific expansion history our universe experienced. This factor encodes decades of detailed cosmological observations and theoretical understanding distilled into a single number. Understanding why the observable universe is 93 billion light-years across rather than 50 or 200 requires understanding this entire cosmic history. The size is not arbitrary, but follows from the universe's age, composition, and expansion history, all measured through careful observations. This interconnection of cosmic properties is one of modern cosmology's great achievements. Different observations of different phenomena all converge on a consistent history. Supernova distances, CMB fluctuations, galaxy clustering, light element abundances all tell the same story when analysed through the framework of expanding universe cosmology. The observable universe's size is thus both a conclusion from this framework and a constraint on it. The size must be consistent with all other observations. Any proposed cosmological model must predict an observable universe of approximately the measured size, or it's ruled out. This self-consistency provides confidence that the framework is correct, even where uncertainties remain. The 93 billion light-year diameter represents the culmination of the universe's 13.8 billion year history of expansion, encoded in a single spatial extent. Every time we state this size, we're implicitly referencing the entire cosmic history that produced it. The observable universe's finite extent raises profound questions about infinity, both mathematical and physical, that philosophers and cosmologists continue to grapple with. A finite observable universe doesn't imply a finite actual universe. As discussed, the universe beyond our horizon might extend infinitely. But what does infinity mean in a physical context? Is it merely a useful mathematical concept, or can actual physical infinity exist? Mathematically, infinity is well defined. The set of integers is infinite. The number of points on a line is infinite. These mathematical infinities are essential to calculus and modern mathematics. But physical infinity is more questionable. Can space truly extend infinitely? Can there be infinite matter? Statistical mechanics suggests that in infinite space, fluctuations of any size occur somewhere. This includes fluctuations creating entire observable universe-sized regions. The anthropic principle becomes relevant. We necessarily observe a region suitable for our existence, but in infinite space, infinitely many such regions exist. Why do we observe this particular one? The question has no answer because this one has no meaning in an infinite ensemble of identical regions. This can seem unsettling philosophically. It suggests our observable universe, while finite and unique to us, is merely one among infinitely many identical copies. Some interpret this as reducing cosmic significance. If infinite copies exist, nothing we observe is truly unique. Others argue it doesn't matter philosophically. Whether unique or one of infinitely many, our universe's properties and our existence within it remain meaningful. The multiverse in eternal inflation adds another layer. If inflation is eternal, creating infinitely many causally disconnected regions with possibly different properties, infinity multiplies. Different regions might have different physical constants, or even different effective laws of physics, with only some suitable for life. In such a scenario, the observable universe is just one bubble in an infinite inflating space. One of infinite bubbles, possibly one of infinite identical bubbles. The mathematical apparatus for dealing with infinities is well developed. Set theory handles different sizes of infinity. Measure theory deals with probabilities in infinite spaces. But applying these mathematical tools to physical cosmology remains challenging. What does probability mean in infinite space where everything happens infinitely often? The measure problem in eternal inflation is precisely this difficulty. How do you calculate likelihoods when the sample space is infinite? Various proposals exist, but no consensus has emerged. This remains an active research area at the intersection of cosmology and philosophy. For the question of how far the observable universe extends, these considerations of infinity highlight that the 93 billion light-year answer is specifically about observation, not about total extent. The observable universe is finite and well-defined. The total universe might be infinite, but that infinity lies beyond verification. This distinction between observable and total is essential for clear thinking about cosmic extent. Infinity remains theoretically possible but observationally inaccessible. Science works with what can be measured, which is necessarily finite. The infinite, if it exists, must be addressed through theoretical reasoning rather than empirical observation. Whether infinity exists physically or not, the observable universe provides a finite but vast laboratory for studying cosmic properties. 93 billion light-years contains enough galaxies, enough structure, enough phenomena to keep science occupied indefinitely. If the universe beyond is infinite, that infinity doesn't diminish the finite observable region's richness or importance. And if the universe is finite but large, the same conclusion holds. The observable universe represents what we can study, and it's more than sufficient. The infinite, whether real or idealized, remains a subject for mathematical exploration and philosophical contemplation rather than empirical science. But it provides essential context for understanding what the observable universe represents, a finite window on what might be infinite existence. The particle horizon represents a fundamental limit on observation, one that cannot be overcome by technological advance, but is built into the structure of space-time itself. Unlike technological limits that better instruments can eventually surpass, the particle horizon is set by cosmic age and light speed. No matter how powerful our telescopes become, we cannot see beyond the particle horizon. The light from beyond simply hasn't had time to reach us yet. This is different from, say, the limit of current telescope sensitivity. We can build more sensitive instruments and detect fainter objects, but we cannot build instruments that detect a light that hasn't arrived. The particle horizon is absolute. This creates a permanent boundary on empirical cosmology. The observable universe's extent defines the scope of observational science. Some find this limitation frustrating. It means much of the universe, perhaps most or all of it if truly infinite, remains forever beyond direct study. We can theorize about the unobservable universe, but we cannot verify those theories through observation. This is different from most scientific limitations, which are practical rather than fundamental. We can't currently visit distant stars, but there's no physical law preventing it. The particle horizon is different, even in principle, even with perfect technology, even waiting arbitrarily long times. Some regions remain unobservable. Actually, the situation is worse due to dark energy. The event horizon means some regions will never become observable, even given infinite future time. The cosmic event horizon is analogous. It's set by global space-time geometry and expansion dynamics, not by local physics. Some physicists have explored whether these fundamental limits might be circumventable through exotic means. Wormholes, if they exist and can be stabilized, might in principle connect distant regions of space, potentially bypassing the particle horizon. But wormhole physics is speculative. We have no evidence they exist or could be manipulated as transportation devices. More fundamentally, even if wormholes existed, they couldn't allow access to regions beyond the event horizon because those regions are fundamentally disconnected. The causal structure of accelerating expansion prevents any signal, even through wormholes, from reaching us from beyond the event horizon. This illustrates how the horizons are built into space-time structure itself, not merely reflecting current technology or understanding. Improving technology or theory cannot overcome limits set by global causal structure. This has philosophical implications. It means the scope of empirical science is fundamentally bounded. We can never have complete empirical knowledge of the universe because most of it is unobservable. This doesn't make the unobservable universe meaningless for science. We can use observed regions to infer properties of unobserved regions through extrapolation, but those inferences cannot be directly verified. They remain theoretical rather than empirical. Some philosophers argue this limits what we can claim to quote 6 about the universe. Knowledge requires verification, and the unobservable cannot be verified. Others contend that well-grounded inference constitutes knowledge even without direct observation, and that demanding direct observation of everything is too stringent. For cosmology practically, the particle horizon defines the playing field. Cosmologists study the observable universe and build models consistent with its properties. Those models make predictions about the unobservable universe. But the unobservable remains inferred rather than measured. This is not a failure of cosmology, but a recognition of fundamental limits built into the universe's structure. The 93 billion light-year observable diameter represents the scope of empirical cosmology, bounded by limits that technology cannot overcome. Understanding these limits is as important as measuring distances within them. It defines what questions cosmology can answer empirically versus theoretically. The particle horizon is thus both a distance measurement and a philosophical statement about the bounds of empirical knowledge in an expanding universe. The observable universe's extent has profound implications for understanding humanity's place in the cosmos, providing perspective on our significance and cosmic context. The 93 billion light-year scale is so vast that it defies intuitive comprehension. No human will ever traverse even a tiny fraction of this distance. The fastest spacecraft we've sent, travelling at about 17 kilometers per second, would take over 150 trillion years to cross the observable universe. This is roughly 10,000 times the current age of the universe. The distance is effectively infinite from the perspective of human experience, yet it's finite and measurable. We can calculate this distance precisely, understand why it has the value it does, and contemplate its implications. This combination of untraversable vastness and precise knowledge characterizes modern cosmology. We cannot reach, but we can understand. The observable universe contains roughly 2 trillion galaxies, based on deep field observations and extrapolations. Each galaxy contains typically hundreds of billions of stars. The total number of stars in the observable universe is roughly 10 to the 24th power. This is a billion trillion trillion, a number so large that even analogies fail to convey it meaningfully. Each star likely has planets based on exoplanet surveys showing planetary systems are common. The number of planets might exceed 10 to the 24th power as well. Some fraction of those planets are potentially habitable. The Drake equation and related frameworks attempt to estimate how many might host life. Even if life is extraordinarily rare, in 10 to the 24th planets, it might exist in millions or billions of locations across the observable universe. This vastness provides perspective on Earth's cosmic significance. We're one planet orbiting one star in one galaxy among trillions. From a cosmic perspective, Earth is utterly insignificant in size and location. We occupy no special place, follow no privileged trajectory. This can seem diminishing. If the universe is so vast and we're so small, what meaning can our existence have? But significance doesn't come from size or cosmic position. It comes from complexity, consciousness, and the capacity for understanding. Humans might be tiny and cosmically unremarkable in location, but we're the only known beings capable of measuring the universe, contemplating its extent, and understanding its nature. This capacity for comprehension is itself remarkable. Creatures evolved on one small planet can determine the universe's age, size, composition, and history. We can trace causation back to the Big Bang, forward to the cosmic future, outward to the particle horizon. No other entity we know of can do this. In this sense, humans are significant not despite cosmic vastness, but in relation to it. The observable universe's scale also provides context for Fermi's paradox. Where is everybody? If life is common and intelligence emerges readily, where are the signs of other civilizations across 2 trillion galaxies? The vast distances might be part of the answer. Even if civilizations exist, communication across millions or billions of light years would be extraordinarily challenging. Signals would take longer than civilization timescales to traverse cosmic distances. The universe might be full of isolated civilizations that never contact each other. The particle horizon creates ultimate isolation. Civilizations beyond our horizon are forever undetectable, no matter how powerful their signals. Even within the observable universe, the sheer scale makes contact unlikely on human timescales, unless civilizations are extremely common. The 93 billion light-year extent thus frames the scope of possible contact and interaction. Even if we're not alone, we might be functionally alone due to cosmic vastness. This scale also affects thinking about humanity's long-term future. If we survive and expand beyond Earth, how far might we spread? Even at relativistic velocities, reaching the local group's edge would take millions of years. Reaching neighbouring galaxy clusters would take tens or hundreds of millions of years. The observable universe is far beyond any realistic expansion capability. We might eventually spread through the local group, but not much farther. Dark energy ensures that most of the observable universe will recede beyond reach before we could possibly reach it. The cosmic future will be lonely, with humanity confined to whatever region it can colonize before cosmic acceleration isolates structures. This provides perspective on cosmic ambitions. The observable universe is vast beyond our reach, even in imagination. We can observe and understand, but cannot travel to, or meaningfully affect most of what we see. This limitation might seem disappointing, but it also focuses attention on what's achievable. Understanding through observation rather than exploration through travel. The 93 billion light-year observable universe is humanity's to study but not to traverse. It provides endless scientific opportunity but no expansion destination. Understanding our place in this vast cosmos means acknowledging both our physical smallness and our intellectual capability to comprehend scales far exceeding our direct experience. This is the paradox of modern cosmology. We're insignificant in cosmic extent, but significant in our capacity to understand that extent. The observable universe's size thus matters not for practical purposes, but for philosophical and intellectual ones, framing how we think about ourselves, our significance, and our cosmic context. One of the most conceptually challenging aspects of the observable universe's boundary is understanding that it's an edge from our perspective, but not an edge in space itself. Standing at the centre of the observable universe, our position, we see a sphere extending 46 billion light-years in all directions. This sphere has an edge, the particle horizon, beyond which we cannot currently observe. But someone located at our particle horizon, looking outward from their position, would see their own observable universe extending 46 billion light-years in all directions from them. Their observable universe would include regions beyond our particle horizon, invisible to us, but observable to them. From their perspective, we would be at the edge of their observable universe, while they're at the centre of theirs. This illustrates that the particle horizon is observer-dependent. Every location in the universe has its own observable sphere. These spheres overlap partially. Nearby observers have nearly identical observable universes. Distant observers have partially overlapping observables. Observers beyond our particle horizon have completely non-overlapping observable universes. We cannot see anything they see, and vice versa. This creates a network of overlapping observable spheres throughout space, each centered on a different location. There's no universal edge to space in this picture. Each observer has an edge to their observations, but that edge is different for different observers. The particle horizon is thus not a physical boundary in space, but a limitation on observation from a given location. Space presumably continues uniformly beyond all particle horizons. The edge exists only relative to specific observers. This is similar to Earth's horizon. Standing on a beach, you see an ocean extending to the horizon. That horizon appears to be an edge of the ocean, but someone at your horizon looking outward sees ocean continuing beyond, with their own horizon farther out. The ocean has no edge at your horizon. Your horizon is merely your viewing limit, not a boundary of water. Similarly, the cosmic horizon is our viewing limit, not a boundary of space. This observer-dependent nature of horizons is characteristic of relativity. Different observers in different states of motion or at different locations experience different horizons. For the cosmic particle horizon, the relevant difference is location in space and time, not motion. Observers at different cosmic locations have different horizons. Someone 10 billion light-years away from us sees a particle horizon centered on them, extending 46 billion light-years from their position. Their horizon sphere includes regions beyond our horizon. The two spheres intersect but don't coincide. If we could communicate with them, sending signals at light speed, we could learn about regions beyond our particle horizon that are within theirs. But such communication would take 10 billion years each way, making it impractical, and regions beyond both our horizons would remain mutually inaccessible. The overlapping horizon structure has interesting implications for cosmic communication hypothetically. A network of observers spread throughout space could in principle share information about regions beyond any single observer's horizon by communicating with intermediate observers. But the time delays would be enormous, and the network couldn't extend beyond anyone's event horizon. With accelerating expansion creating event horizons, some regions are fundamentally beyond reach, even through multi-step communication. The edge that isn't an edge concept also relates to cosmic isotropy. The CMB looks the same in all directions from our position. This suggests we're not in a special location. But if we're not special, observers at the CMB surface looking toward us should also see isotropy. Their observable universe should look similar to ours, supporting the cosmological principle that all locations are equivalent. This self-consistency is important for cosmological models. If the observable universe looked very different from different locations, it would violate homogeneity. The fact that horizons are observer-dependent rather than physical boundaries helps maintain this consistency. The particle horizon's nature as a viewing limit rather than space boundary also affects thinking about what's real. If regions beyond our horizon exist but are unobservable, are they real? Do they exist in the same sense observable regions do? Philosophically, this is the problem of unobservable entities. Science typically treats entities as real if they're observable or have observable effects. Regions beyond the particle horizon have no current observable effects on us. They're real in the sense of existing, but not real in the sense of affecting us. Different philosophical positions treat this differently. Realists might say they exist independently of observation. Instrumentalists might consider them theoretical constructs. For practical cosmology, regions beyond the horizon are real in the sense that space continues, and presumably contains matter and structure. We infer their existence from the universe's observed homogeneity, and from theoretical understanding that space doesn't end at observation limits. But we acknowledge they're beyond empirical verification, placing them in a different epistemic category than observed regions. The edge that isn't an edge concept thus highlights the complex relationship between observation, reality, and cosmic structure. The observable universe has a boundary, but that boundary is a limitation of observation rather than a limit of existence. Understanding this distinction is crucial for thinking clearly about cosmic extent and what it means when we say the observable universe is 93 billion light-years across. That's our observational sphere. Not necessarily the extent of all that is. The observable universe's finite extent raises profound questions about the limits of knowledge and what aspects of cosmic reality must remain forever unknown. Some limitations are practical. We cannot currently observe galaxies at extremely high redshifts because our telescopes aren't sensitive enough, but future instruments will detect fainter objects, extending our observational reach to earlier cosmic epochs and greater distances. These practical limitations are temporary, overcome by technological progress. But other limitations are fundamental. Regions beyond the event horizon will never become observable, regardless of technological advance or waiting time. This creates permanent boundaries on knowledge. We can never empirically verify properties of regions beyond the event horizon. We can theorize about them, make models, use physics to infer their properties, but we cannot observe them to test our theories. This is a fundamentally different kind of limitation than the practical obstacles science normally faces. It means some questions about the universe have no empirical answer, even in principle. How large is the total universe? If beyond our horizon, we cannot measure it. Is it finite or infinite? Observations cannot distinguish if both extend beyond observability. What is happening right now at the observable universe's edge? We can never know now at a distance because observation requires light travel time. We see those regions as they were tens of billions of years ago. Their current state is beyond observation. Do the laws of physics remain the same beyond the horizon? We assume they do based on homogeneity. But we cannot verify this assumption. Perhaps distant regions have different physical constants, or even different effective laws. We'd never know. Are there other universes, causally disconnected bubbles in an infinite space? Eternal inflation predicts this, but if beyond our event horizon, they're unobservable. These questions illustrate the permanent limits on empirical knowledge created by cosmic horizons. Science works by testing theories through observation, but theories about unobservable regions cannot be tested. They remain metaphysical rather than physical, interesting but not falsifiable. Some scientists are comfortable with this limitation, viewing it as defining the proper scope of empirical science. Science studies what can be observed. The unobservable belongs to philosophy or mathematics, but not empirical investigation. Others find it more troubling, arguing that if significant aspects of reality are unobservable, science's reach is fundamentally limited. We might develop seemingly accurate theories that work for observable regions but fail for unobservable ones, without any way to detect the failure. This could mean our best cosmological models are wrong about the total universe, even while fitting all observations perfectly. There's no resolution to this tension. Both positions have merit. Science's self-limitation to the observable is both strength and limitation. For specific examples, consider dark energy. We've observed its effects within the observable universe through accelerating expansion. But does dark energy exist beyond the observable universe? We assume it does based on homogeneity. But if it varies far beyond observation, we'd never know. Our dark energy theory might be incomplete, describing only local properties while missing crucial aspects apparent only at super-horizon scales. Similarly, consider inflation. Inflation theory fits many observations: flatness, homogeneity, density fluctuations. But inflation predicts a universe vastly larger than the observable region. We can never verify this prediction observationally. If inflation is wrong about superhorizon scales while right about observable ones, we cannot detect the error. These limitations mean cosmology, despite great success, deals with a small, possibly infinitesimal, fraction of total reality. The observable universe might be to the total universe as a single atom is to the Earth, or even less. All our cosmological knowledge might describe just one tiny patch of an incomprehensibly larger whole. This should inspire humility. The confidence with which we discuss the universe should be tempered by awareness that we mean the observable universe. The total universe might be radically different from our observable sample if we're unlucky in our cosmic location. But absent evidence for differences, assuming similarity is the most reasonable approach. Science proceeds based on available evidence. We cannot let unverifiable possibilities paralyze investigation. We study what we can observe and make reasonable inferences about the rest. The fundamental unknowns will remain unknown. Future generations will have the same limits we face, perhaps extended slightly but not eliminated. Some aspects of reality are simply beyond empirical science's reach, due to the universe's structure and our location within it. Accepting this limitation is part of mature scientific thinking. Science is powerful, but not omniscient. There are questions science cannot answer, not due to current ignorance, but due to fundamental constraints on observation. What we can never know includes the total extent of the universe. Whether space is truly infinite, what exists beyond all horizons, and whether cosmic properties vary at super-horizon scales. These permanent unknowns don't diminish science's achievements, but contextualize them within appropriate epistemic boundaries. The 93 billion light-year observable universe represents what we can know empirically. Beyond lies the forever unknowable. Understanding how far the observable universe extends requires not just observation, but mathematical framework describing cosmic geometry and expansion dynamics. The mathematics of cosmology is general relativity, Einstein's geometric theory of gravity relating space-time curvature to matter and energy. For cosmology, assuming homogeneity and isotropy dramatically simplifies Einstein's equations, producing the Friedmann-Lemaitre-Robertson-Walker metric. This metric describes expanding homogeneous universes and is the foundation for modern cosmology. The metric contains a scale factor describing how distances change with cosmic time. All physical separations scale with this factor. The metric also includes a curvature parameter taking values representing positive, 0, or negative spatial curvature. Observations strongly support zero curvature, a spatially flat universe, which simplifies calculation significantly. The Friedmann equations, derived from Einstein's equations using this metric, govern how the scale factor evolves over cosmic time. These equations relate the expansion rate to energy density and curvature, showing how expansion depends on the universe's energy content and geometry. The equations also describe acceleration, revealing that ordinary matter causes deceleration, while negative pressure from dark energy causes acceleration. These equations, combined with conservation of energy, determine how the universe evolves given its energy content. Different energy components evolve differently as the scale factor changes. Radiation density decreases with the fourth power of the scale factor, because both number density and energy per photon decrease. Matter density decreases with the third power as volume increases but particle energies stay constant. Curvature contributions decrease with the second power. Dark energy as a cosmological constant remains constant density as space. Expands. These scaling relations mean different components dominate at different epochs. In the early universe, when the scale factor was small, radiation dominated. As the scale factor grew, matter became dominant. Recently, dark energy has taken over. The transition epochs determine cosmic evolution and the observable universe's size. To calculate the particle horizon, cosmologists integrate the light travel distance over cosmic history, accounting for how the scale factor changed at each moment. This integral cannot be solved analytically for realistic energy content but is easily computed numerically. The result depends on cosmological parameters, the current expansion rate, matter density, radiation density, and dark energy density. Current best fit values give approximately 46 billion light-years for the particle horizon in comoving distance. The mathematics also describes the relationship between redshift and distance. Light's wavelength stretches with the scale factor as space expands. Redshift measures how much the scale factor has grown between emission and observation. For the CMB with redshift approximately 1090, the scale factor when emitted was about 1/1091st of today's value. Converting redshift to distance requires integrating the expansion history, with the expansion rate at each redshift determined by the Friedmann equations and energy densities. This integral gives proper distance as a function of redshift. Different cosmological distance definitions exist: luminosity distance, angular diameter distance, comoving distance. All are related mathematically but give different numerical values. For the particle horizon, comoving distance is most relevant. This is distance measured at present cosmic time accounting for expansion. The mathematics elegantly connects observations like redshifts, angular sizes, and brightnesses to physical distances and cosmic history. Different universe geometries give different results. A closed universe with positive curvature would give smaller particle horizon. An open universe with negative curvature would give larger horizon. But observations constraining curvature near zero mean flat space formulas apply. The mathematics also reveals why recession velocities can exceed light speed. Recession velocity equals the expansion rate times distance. For large enough distance, this exceeds the speed of light. There's no contradiction with relativity because this isn't motion through space, but expansion of space. Special relativity limits velocities through space, but doesn't constrain how fast space can expand. The mathematics of cosmology is thus essential infrastructure for determining the observable universe's extent. Without general relativity in these solutions, we couldn't connect observations to distances or calculate horizons. The 93 billion light-year diameter emerges from solving these equations with measured cosmological parameters. The mathematics transforms raw observations into cosmic understanding, revealing the universe's geometry, history, and extent through elegant theoretical framework. Understanding these mathematical foundations deepens appreciation for the observable universe's size as not merely measured, but calculated from first principles based on how gravity curves space-time and how energy drives cosmic expansion. Having explored how far the observable universe extends in our actual universe, it's instructive to consider how the answer would differ in alternative cosmic scenarios. If the universe were not expanding, the particle horizon would be much smaller. With static space, light travel distance equals age times light speed. A static 13.8 billion-year-old universe would have particle horizon radius of 13.8 billion light-years, not 46 billion. The observable diameter would be 27.6 billion light-years, about 3 times smaller than reality. This illustrates how crucial expansion is for the observable universe's size. Most of the extent comes from expansion stretching distances. If expansion were faster throughout history, the particle horizon would be even larger. Faster expansion means the Hubble sphere grew faster, allowing light from more distant regions to enter and reach us. Conversely, slower expansion gives smaller particle horizon. The specific value depends on detailed expansion history. If the universe were younger, the particle horizon would be smaller proportionally. A 7 billion-year-old universe would have roughly half the observable extent. The relationship isn't precisely linear because expansion rate changes with time, but younger universes are smaller in observable extent. If dark energy were stronger, causing faster acceleration, the event horizon would be closer. Less of the universe would ever become observable. Stronger dark energy means more rapid future acceleration, preventing light from ever reaching us from beyond a smaller event horizon. If dark energy were weaker or absent, the event horizon would be farther, possibly infinite if expansion decelerated forever. In a matter-only decelerating universe, eventually light from arbitrarily distant regions could reach us given enough time. If the universe had significant spatial curvature, horizon calculations would change. Positive curvature in a closed universe gives smaller horizon than flat. In a closed universe, space wraps back on itself at some finite distance. The particle horizon cannot exceed the universe's circumference. If the universe was small enough, less than the flat space horizon, we might see the same structures in multiple directions as light travelled around the universe. Negative curvature in an open universe gives slightly larger horizons than flat space, though the difference is modest for small curvature. If inflation never occurred, the early universe would be much smaller. Without inflation's rapid expansion, the horizon problem wouldn't have a solution. Regions visible in the CMB would not have been in causal contact before recombination, making their uniform temperature mysterious. The observable universe might still be roughly the same size determined by subsequent expansion history, but initial conditions would be different and more difficult to explain. If the universe was cyclic, contracting and expanding repeatedly, the particle horizon concept becomes more complex. In each cycle, light could only propagate during that cycle, but multiple cycles might allow information to transfer between cycles in some models. This could potentially allow observation of effects from before the current Big Bang, though most cyclic models don't permit this. If we lived in a universe with different dimensionality, the mathematics changes entirely. 4 spatial dimensions would have different geometry and expansion dynamics. More dimensions typically make gravity stronger at given scales, affecting structure formation and expansion rates. The observable extent would depend on these modified dynamics, likely being different from our 3-dimensional universe's value. If the speed of light were different, the particle horizon distance would scale proportionally. Faster light gives larger observable universe. Slower light gives smaller. Though fundamental constants like light speed might seem arbitrary, changing them often affects other physics in connected ways. If physics were such that electromagnetic radiation didn't exist, the concept of an electromagnetic observable universe would be meaningless. But gravitational waves or neutrinos might provide alternative observation methods with different horizons. If we lived in a multiverse with different regions having different physics, our observable universe would be the region within our horizon sharing our physics. Adjacent regions with different constants would become observable only if their light could propagate to us, which might not be possible if physics differs too drastically. These alternative scenarios illustrate that the observable universe's 93 billion light-year extent is not arbitrary, but follows from specific properties our universe possesses. The universe age of 13.8 billion years sets the time light has had to travel. The current expansion rate and its history throughout cosmic time determine how distances have stretched. Spatial flatness simplifies the geometry. Current dark energy density controls recent acceleration. 3 spatial dimensions define the geometric framework. Standard physics, including the speed of light, establishes fundamental limits. Different values for any of these would give different observable extents. Our universe's specific values produce the specific observable size we measure. Understanding how things could be different clarifies why they are as they are, and what factors determine the observable universe's reach. The 93 billion light-year diameter represents our universe's particular combination of properties, not a universal number for all possible universes. While the observable universe's extent is well established at about 93 billion light-years, uncertainties remain, and future observations will continue refining this value. The current uncertainty in the particle horizon distance is roughly 3 to 5%, primarily from uncertainties in cosmological parameters. The largest contributor to uncertainty is the Hubble constant. Different measurement methods give values differing by about 8%. This Hubble tension translates directly to uncertainty in distances. Higher Hubble constant means younger universe and slightly smaller particle horizon. Lower Hubble constant means older universe and larger horizon. The difference could shift the diameter by several billion light-years depending on resolution. Future observations aim to resolve this tension. Projects like the Vera-Rubin Observatory will discover more supernovae, improving local Hubble constant measurements. Next-generation CMB observations will refine early universe constraints on the Hubble constant, sharpening the comparison between methods. Gravitational wave observations of neutron star mergers provide independent Hubble constant measurements. As more events are detected, this method's precision will improve. Eventually, these converging measurements should resolve whether the Hubble tension indicates systematic errors or new physics. Resolution will sharpen the observable universe size determination, potentially to 1 or 2% precision. Dark energy properties also affect the calculation. Current observations are consistent with constant dark energy density, but evolution remains possible. If dark energy density changes with time, the expansion history differs from constant models. This would alter the calculation of particle horizon distance, changing the result depending on how dark energy evolves. Future observations of distant supernovae, baryon acoustic oscillations and weak gravitational lensing will constrain dark energy evolution. If dark energy is constant, precision will improve. If it evolves, models will need modification, and distance calculations will change. Spatial curvature measurements will also improve. Current constraints show curvature very close to zero but not exactly zero. Tighter constraints on curvature will either confirm exact flatness or detect small deviations requiring modified horizon calculations. Planck measurements constrain curvature to about 1%. Future CMB observations might reach 0.1% precision. Subtle effects currently at the edge of detectability might become measurable. For instance, neutrino mass affects expansion history slightly. Summing over neutrino species, their mass contribution influences the matter radiation transition and subsequent expansion. Current limits on neutrino mass allow for variations affecting distances at the percent level. Future measurements will narrow this. Primordial gravitational waves from inflation, if detected through CMB polarization, would provide information about the very earliest expansion. This could refine models of how expansion began, affecting calculations of total cosmic history and integrated horizon distance. Beyond parameter refinements, conceptual questions remain about the observable universe's nature. Is the universe truly infinite beyond our horizon, or finite but large? Observations cannot definitively answer this currently. Future observations might detect topology signatures if the universe is finite and smaller than thought, potentially seeing repeated structures. But if infinite or finite but much larger than observable region, topology will remain unmeasurable. The universe's ultimate fate affects future observability. If dark energy is constant, the scenario of cosmic isolation described earlier follows. If dark energy strengthens, leading to Big Rip, even bound structures eventually are torn apart as acceleration becomes infinite. If dark energy weakens or decays, deceleration could resume, allowing the observable universe to continue growing indefinitely. Current observations favour constant dark energy, but long-term behaviour over trillions of years remains speculative. The observable universe concept itself might need refinement if new physics is discovered. If quantum gravity effects become important at cosmic scales, or if modifications to general relativity are needed, horizon calculations might change. These possibilities are speculative, but science must remain open to paradigm shifts when evidence demands. For now, based on current physics and observations, the observable universe extends 93 billion light-years across with few percent uncertainty. This number will be refined as observations improve and theoretical understanding deepens, but dramatic changes are unlikely unless major surprises emerge from future observations or theoretical breakthroughs. The question of how far the observable universe reaches thus has a definite answer that will be incrementally improved but probably not revolutionized. Future cosmologists will know the distance more precisely, understand it more deeply, and perhaps extend observations slightly farther. But the fundamental framework, the finite observable region, in a possibly infinite universe, bounded by horizons from cosmic age and expansion, will likely remain. The 93 billion light-year scale represents current best knowledge, refined over decades, and provides a foundation for continued investigation. Thank you for journeying with me through this exploration of cosmic boundaries, this patient investigation of how far the observable universe actually reaches. I hope you found peace in understanding that even infinity can have edges from particular perspectives, that vastness can be measured even when untraversable, and that boundaries can be fundamental yet not absolute. The observable universe extends 46.5 billion light-years in every direction from where you are right now. This creates a sphere 93 billion light-years across, containing everything we can possibly observe with electromagnetic radiation. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released its need to grasp incomprehensible scales. The distances we've explored perhaps help you feel both infinitesimally small and profoundly significant, a tiny observer comprehending vastness beyond experience. Sleep well tonight, knowing you inhabit not just a planet or solar system or galaxy, but an observable universe 93 billion light-years across, larger than simple light travel time would suggest, because space itself has been expanding for 13.8 billion years. Beyond this observable sphere, space likely continues, perhaps infinitely, forever beyond our reach but not beyond our understanding. Dream peacefully of horizons that aren't edges, of boundaries determined by light and time, of an expanding cosmos carrying distant galaxies beyond observation. Dream of the cosmic microwave background sphere surrounding us, light from just after the Big Bang finally reaching our eyes. Dream of the event horizon in our future, limiting what we'll ever observe as dark energy accelerates expansion. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed, and may you carry forward an appreciation for the observable universe's definite extent, for the fundamental limits on observation that create cosmic horizons, and for humanity's achievement in measuring distances beyond physical reach. How far does the observable universe actually reach? 46.5 billion light-years to the particle horizon, 93 billion light-years across, finite, measurable, vast beyond comprehension, yet precisely known through patient observation and careful calculation. Good night.